Hello everyone. In today's video, I'm going to show you how you can train your own speech command classification model. Just like in my YOLO video, I'm going to be mixing a little bit of an existing data set with my custom uh, audio files. So you can go on Kaggle and download a speech command data set and unzip it, and you're going to have all the classes you need. Now, you may or may not use all of the classes. It really depends on what you want to do, but it's definitely a good thing to have a good amount of different voices and people, pronouncing the different words. And if you want to add your own specific word, then you have to record your own audio. And I typically just use the regular vocal recorder of Windows. And all I do is I just make sure that I save the files as WAV files. Because in artificial intelligence for audio, it's typically most of the time uh, the audio is saved as WAV files. On my GitHub, you're going to find these three files in utils, allowing you to pre-process the audio. Audio split is for if you record your own samples. Let's say that you just record, you repeat a word again and again, every 1 second, and it's going to be a long audio file. Then you can use this script to split that into little chunks. And after that, what you want to do is pre-process the audio files that you have, whether it's your custom audio files or the one from the dataset. So in my specific case, I want my audio to be 1 second at 16 kilohertz mono channel. And this script allows you um, to make sure that all your audio files respect these conditions. But you can change it to match whatever you want. But typically in AI, it's usually 16 kilohertz as a sample rate or frequency of the audio. And the other characteristic is the number of samples, which gives you the length of the audio. Typically, if you have sample rate times duration, this gives you the number of samples. So for example, for 1 second audio, if you have 16,000 kilohertz times 1 second, you're gonna have 16,000 samples. So this is what corresponds to 1 second at a sample rate of 16 kilohertz. This script is going to go through the folder where you have your audio files and check the sample rate. If it's 16 kilohertz, if it's not 16 kilohertz, it's going to resample your audio to be 16 kilohertz. And the next thing, it's going to check the number of samples. If you have uh, the 16,000 samples, that's an option. The other option, which I don't necessarily recommend, is if you don't have the target number of samples, you can either truncate or pad the audio file. Let's say you have something like 14,000 instead of 16, so you're just going to buffer it up a little bit so that it gets the right length. Or if it's above, shorten it a little bit. Now, it really depends on your data set. And if you have something like 2000 samples, for example, that's a very, very short audio. And if you end up buffering it to 16,000, you pretty much end with a silence file. And if you incorporate that into your training, it's just going to be very disruptive. So I just recommend dropping any file that isn't the right length. And the final step will be to, if you have a stereo, so left and right, two channels, it's going to fuse that into mono. Typically, In AI, it's mono, at least for training that's used. And this part of the code is just to keep track of how many files were skipped, the files that didn't match uh, the criteria that we had. And finally, you have this create labels script that just that will match the audio with the class it belongs to. And here I'm using the underscore to just be able to make the correspondence. But you can change it, everything is open source here. You can do whatever you want. That's just an example I'm giving you. And for this demo, I'm going to create a small data set with a few samples that I'm going to pick. So let's take dog. So here I'm going to rename that so that it works with my create labels file. Here I have 4 different classes, 3 that I picked from the data set, and this is my custom word alphatron. Now I'm going to use the pre-processing script on my small data set. And this is our output folder containing the files formatted in the correct way. Now I'm going to create the labels. And as you can see, an audio, and in front you have the class it belongs to. And with this, we are ready to train. Now, why are we doing all of that formatting? Is because when you're using neural network, I think it's specific to convolutional neural network, I'm not sure, but you have this thing in Pytorch, which is the collate function, that makes sure that within a batch, all of the samples have the same shape, that the tensor is the same. So in a batch, you cannot have something that's has a length of 1 second and another thing has 2 3 seconds, or 500 milliseconds, or something that has a mono channel and another one is stereo. Everything has to be the same. I'm just gonna remove a few comments and change a few things. I ran training for an epoch to comment on the tensors later on. So here you have all the libraries. This one is the class that allows us to load the data set. There's nothing much to say here. I would say it's basic software. This function here is an interesting one because it allows us to get the weights, the class weights. It's not the dynamic class weights that are updated during training. Those are fixed weights, which represent, I would say, the percentage of different classes relatively to each other in the data set. So it allows us to know, which class is overrepresented or underrepresented. It gives coefficients so that when we train, on an unbalanced data set, uh, the loss function is going to focus more on the underrepresented classes and focus less on the overrepresented ones. So it's an interesting method to use when you have an unbalanced data set. And in AI, if you can avoid to have an unbalanced data set, please do, because it makes training easier when everything is balanced. But even with a balanced data set, you can still use uh, these fixed class weights that are calculated by a method called inverse frequency. Here is our CNN. I'm going to talk about that later. And here are the different functions. This one to train, validation, which allows us to run inference on the validation data sets to assess how well our model is doing on scene data. This is a early stopping mechanism. So whenever the model starts to overfit, which means it loses the ability to generalize, it's gonna automatically stop training after a given number of epochs. If we go down here, we can see the transformations that are applied to the audio files. And here we have what's called a Mel Spectrogram. Basically, it transforms the audio into an image. If we look at the characteristics, you have the sample rate 16 kilohertz, number of Mel beans 64. For speech recognition, it's typically, it's 40 Mel beans, 64, 80 Mel beans. The higher the number of Mel beans, the better the quality of the image. And another important parameter is the number of fast Fourier transform, which also has an influence on the frequency resolution. But the clarity of the image really depends on the number of Mel beans. And you have the hop length, which is the way the frames are constructed, the way the frames are sliding to create the entire Mel spectrogram. And typically the value of the hop length is usually NFT or window size divided by 2, because what's important when you create a Mel spectrogram or any spectrogram for the matter is overlapping. You typically want 50% overlapping. So usually it's divided by 2, but you can also have 75% overlapping, divided this value divided by 4. Here I'm a little bit over 4, because the lower the hop length, the better, the more information, the more temporal information you have. So to get more temporal information from the audio file, I lower the number of hop lengths, and the direct effect is I'm gonna get more frames. Here we have amplitude to decibel to convert the Mel spectrogram from the linear scale to the logarithmic scale, to make it more human-like, because human beings, we hear sound in the logarithmic scale. So if we want to create an AI model that's going to interact with us, we want it to hear things the way we hear it. Here I'm doing what's called data augmentation. So I am twisting a little bit the Mel spectrogram so that during training, the model can adapt to some subtle changes in the audio file. Well, in the Mel spectrogram, because we've already transformed it. But I'm not applying this augmentation on the validation dataset. When we apply a Mel spectrogram to an audio signal, whether it's with Touch Audio or Librosa, which is a library for audio processing, the default method is what's called center alignment. Briefly speaking, center alignment allows us to catch more details from the original audio signal. And the equation for how many frames you get after transforming the original audio is given by this. So the number of samples of your original audio, so 16,000 samples plus the hop length divided by hop length. So in my case, it's going to be 16,400 divided by 400, which gives me 41 frames. And ironically, when you're looking for the number of frames that you get after applying a Mel spectrogram, you typically find the equation for the left alignment method. But as I said, the one that's used the most and the default one is center alignment. Let's go back in our code and look at what we have. This here is the input tensor of our CNN. So if we look at that 4D tensor, the 4 here represents the batch size, which is here. So 4. This is the number of channels. So the Mel spectrogram is a grayscale image. So in terms of channels, it has only one channel. This 64 is the 64 Mel beans, and this is the 41 frames I was talking about. So this is typically the height of our image, the y-axis, and this, the number of frames, is the width, the x-axis. So all our audio files that are transformed into Mel spectrograms will have this shape. And we don't have any error because we did all the pre-processing beforehand. Now let's take a look at the CNN. And if you want a better understanding of convolutional neural networks or artificial intelligence in general, I recommend watching Code Basics. He's basically artificial intelligence daddy. His explanation of things is very, very clear, easy to understand, and I mean, just check what he does if you're not already subscribed or you don't know who he is. So here I have one channel, which means the Mel spectrogram grayscale image. Number of classes is going to be my output. This is an arbitrary number of filters, or the number of kernels I'm going to use. So the first convolutional layer, one channel, I'm going to apply 32 kernels of size 3 by 3 and a padding of 1. When we apply padding, we're just buffering up the image. There is no relevant information that we are adding. We're just making it bigger. And padding works in a symmetrical way. If you apply padding on the x-axis, whatever the value is, it's going to happen on the left side and on the right side. And if you do that on the y-axis, it's going to happen on the top and the bottom. So it's always whatever value you apply times 2. And in my case, let's say here we have the height or the width, whatever. If I apply a padding of 1, it's going to be 2 here. My kernel is 3. And the stride is the way the kernel moves over the image. By default, the stride is 1. And at the end, you have a +1. And if you do the math, you'll see that after I apply my convolution, what I get is I get a feature map that has the same size as the original image. So there is no shrinking, no reduction happening. Here I have bias equals false because I'm using a batch norm layer. The batch norm layer is a regularizer. It's not a top tier regularizer like the dropout, but it does help. And the thing is, batch norm applies bias itself. So by default, this has bias because when you have a neuron, it's input times weights plus bias. So we're typically not having a batch norm layer is not an obligation. So it makes sense that by default we have bias here. But since bias will come from my batch norm, I don't need the bias that comes from the convolution that we have here. But you can keep both, it's not harmful. But just to save a little bit of computational power, I'm just deactivating the bias from here. because it's redundant. And then after doing my first convolution, I do a second one with the same characteristics, but here I'm pooling using max pooling. So I'm reducing the dimension here by 2. Third convolution, but here I have 64 filters instead of the original 32. So here 32, then the input of the second is going to be the output of the first, etc., etc. So here I have my 32 filters that come from this one, and then I apply 64 kernels here, and I'll get 64 feature maps. And the 64 kernels from this one, I apply again 64 kernels to have 64 feature maps again. And I perform pooling one last time. And in Pytorch, you have this distinction between, let's call it the definition of the different layers. And here is where we actually perform the forward pass. And that's where you're going to add things like the ReLU activation function. So if we go down here, we can have now an understanding of what's going on. So this is the input, and what happens here is after the fourth convolutional layer, we have our 64 channels or 64 feature maps. And this, remember, we've reduced it 4 times. So 64 divided by 4, 16. And here's the same thing, 41 divided by 4, 10. And before getting into the fully connected layer, into the classification part, we perform global average pooling. This operation, at the end of the fourth convolutional layer, we have 64 feature map, and these 64 feature maps have a height of 16 and a width of 10. So uh, we have 16 times 10 neurons per feature map. So you do 16 times 10 times 64, and that's a lot of things. And by applying global average pooling, we are reducing each feature map into a singular value. So we don't have height and width anymore. Everything is reduced to 1 because it's a single value. And after that, we can flatten it and get a 64, a vector of size 64. And from here, it's going to become the input of our first fully connected layer. And between this and the second fully connected layer, I apply a dropout layer. And dropout is actually the most, I mean, maybe not the most, but it's definitely a very good regularizer that you can have. It allows your model to train better without overfitting too quickly by deactivating randomly some. Here I'm using 30% by deactivating 30% of the neurons. So here I have the 64, and then I go up to 128. I apply dropout, and then I reduce to the output classes that I will have at the end, and I return my raw logits. And one last thing about dropout is dropout, you typically apply that in the classification part where you have the fully connected layers, not in the feature extraction part with the convolutional layers, because dropout can be very disruptive during that feature extraction. And if you train your model with dropout layers in the convolutional part, then the accuracy of your model is going to suffer from that. So it's a very good, the best practice is to leave it in the fully connected part of your neural network, and you don't apply any kind of transformation on the last fully connected layer. No ReLU, no dropout, no batch norm. You just leave it the way it is, because this is what outputs the classes, your logits that would then be passed to your loss function. And since we are doing multi-classification, it's going to be a softmax I mean, it's going to be cross entropy loss that I'm going to use. And cross entropy loss applies softmax and all the necessary transformations. And that's why here I'm just returning the raw logics. Here we have two options to train a model. You can use regular cross entropy loss, or you can use the weighted cross entropy loss with the fixed weight I was talking earlier. And the weighted cross entropy loss gave me the best results. And I had faster convergence, which means, the model had very good results after just a few epochs compared to the regular cross entropy loss. But this was not bad at all, but this is just better. So this is the regular one, so I'm not going to explain that. I'd rather come talk about, the weighted one. And here you can see that we're loading the dataset with the class that's defined on top there. And we are splitting the dataset inside Pytorch. For those who've watched my YOLO video, the split was done outside, it was on the disk. But here, everything is handled by Pytorch. So here we have the training dataset and the validation dataset. And we calculate the class weights of the training dataset only because, that's what's important, the training dataset. The validation dataset is there to just, give us the metrics to see how well our model is doing with unseen data from the validation dataset. For training, I have this loss, and for validation, I have this other loss, a regular cross entropy. So here I'm not using the class weights, and even if I had to use the class weights, it will be the class weights of the validation dataset, which I don't calculate. But if I had to do that, it wouldn't have been a good thing because it will have biased my results, because by doing that I will have been helping the model a little bit by telling it, oh, you see, this class is overrepresented and this other one is underrepresented, so you should pay more attention or less attention to this or that other class. But when I leave it like this, I have a more objective result. And earlier in the convolutional neural network, I was talking about the regularizers. So these batch norm and dropout are the regularizers within the CNN, and you have the regularizers that you have outside of the CNN. So here I'm using my optimizers, Adam W, Adam with wave decay. And this wave decay thing is the regularizer that penalizes the strong weights when backpropagation is performed. And here you have the scheduler. So with this, we are reducing the learning rate after a certain number of epochs. And by reducing the learning rate, we allow the model to train better. At the very end here, you can use this to convert the Pytorch model into an ONNX model. The great thing with ONNX is it works a little bit like a Docker container, allowing you to deploy the model on pretty much any electronic device or any platform. So I think it's a good thing to, to incorporate that. Just make sure that you run the cell containing the speech command CNN class. Otherwise, it's not going to work. If you go on my speech command repository, you'll see that I've already put the scripts for inference. But this is going to be for part 2 of the video. But, you can already start to have fun with that if you want. So see you very soon for the inference. Thank you for watching.